All right. So let's finally talk about elliptic equations. So elliptic equation is another special case for the advection diffusion equation where our time derivative term and the advection term are both equal to 0. So what we get is only partial square u partial x squared plus f is going to be equal to 0. Right? Of course, this is just an ODE if we look at one spatial dimension. So let's add on top of this second spatial dimension, which doesn't really change any of the characteristics of this equation. Now we already know everything about how to discretize this equation, right? So we have a two-dimensional, in this case we have a two-dimensional grid. Let's stick to orthogonal grid for now. And our solution is going to be stored again on the grid points. So this is ij, this is I plus 1j, this is I minus 1j, this is ij plus 1. So let's say this is the y plus y direction plus x direction. So this is ij minus 1. And we also have I minus 1, j minus 1 if you want to use it, right, for some derivatives. All right. Okay, so let's discretize both the x and y directional differential operators, and it's very straightforward. So this at I and j, it's just equal to u of I plus 1 plus u of I plus 1j, I minus 1j minus 2uij divided by delta x squared. And let's assume delta x equal to delta y for now. Then my partial square u partial y square is going to be pretty much the same thing, except for j is going to be the one that has plus 1 minus 1 in it. So add these two together, it's going to be the Laplacian operator for two-dimensional solution, right? So this is the Laplacian for u. Okay. Now the primary thing we want to discuss is oh, by the way, the approximation error you can analyze using exactly the same way we did for heat equation. Okay. So the primary thing we want to discuss is how to solve this equation, right? So let's start with a rectangular domain. So we start with a rectangular domain. We first want to derive what is the matrix form of this differential operator. So here we want to again put our solution into a vector. This vector is going to start with u of I equal to 1, j equal to 1. If you code in Python, you may want to say it's u0, 0, but like I'm going to use 1, 1, etc. here. So u1, 2, etc. u1 n minus 1, right? If you are having periodic boundary conditions, that's what we do, right? If we use a Dirichlet boundary conditions, which means we know the value at the boundaries, this is what we do. We remove the values at the boundaries from the unknowns. Then we have u21, etc. u2n minus 1. And u31, etc. goes all the way to un minus 1, n minus 1. So this is my solution vector. It's a flattened array of a two-dimensional array. I want to construct a matrix such that this is going to be equal to my right-hand side. So my right-hand side is going to be what? Let me just write it as plus my f is equal to 0. So f is going to be also discretized. So if I approximate my Laplacian at I and j, then the Laplacian at xij plus f at xij should be equal to 0. So we want to use the same consistent finite difference approximation for f, which just means I want to just store the value of f at these grid points. f(1), etc. f n minus 1, n minus 1, right? Okay, so this is going to be my matrix equation. The only trick is to how do we construct the matrix. So the matrix, let's first take a look at the very first equation, I equal to 1, j equal to 1. So for the first equation, the values outside the boundary is not going to appear in the matrix because they are known values, right? If I have a non-zero boundary condition, it will be lumped into this F11, right? So any non-zero u minus 1j and the u I j minus 1 is going to be divided by delta x squared and getting lumped into this F11, right? Okay, so the only terms I have to consider is this term, this term, this term, and this term. 4 terms. 2 of these 4 terms are diagonal terms. They are together. They are actually the same term. They are both minus 2 divided by delta x squared. So add them together. The diagonal term is going to be minus 4 divided by delta x squared. The next term is I j plus 1. So it's this term. It's going to be 1 over delta x. The next term, j plus 2, it doesn't even appear in the equation. So it's going to be 0, right? So I have 0 and all the way a bunch of zeros until I get to here. I'm multiplying the first row of the matrix with the entire vector to get the first equation, right? So it's going to be a bunch of zeros until I get to this point where the value is 1 over delta x squared again. And then afterwards, nothing going to be appearing in this equation, so I get a bunch of zeros. The second row, I'm looking at I equal to 1, j equal to 2. So the difference is that this additional term is going to be in the equation. This term is going to be here. It's going to be 1 over delta x squared. The diagonal term is the same. The upper diagonal term is going to be the same. I get a bunch of zeros. This is still 0. I get 1 over delta x squared and zeros, right? So what you see is that I'm going to get several diagonals. The main diagonal is always minus 4 over delta x squared. This is always going to be 1 over delta x squared. This is always going to be 1 over delta x squared. And then I have a bunch of zeros in the middle. And starting from the nth entry, right? This is the nth entry. I have another diagonal line that is 1 over delta x squared. Yes? It's yeah, it should be delta y squared. Yeah, but like if I assume a delta x is equal to delta y, then it's the same, right? If you have like in your project, it's going to be more complicated. The diagonal is going to be minus 2 over delta x squared minus 2 times over delta y squared. So you're going to be doing something more complicated. There is also going to be another lower diagonal. So there is a bunch of zeros here until you get to a point 1 over delta x squared again. This is because of this term, right? This is because I have a I minus 1j, which if I look at the equation at grid point I equal to 2, j equal to 1, that corresponds to this very point. So for this particular equation, I have a non-zero entry in the first column of the matrix because of this term. So what I get is I have a matrix. Most of the matrix is going to be 0, but I have five kind of diagonal lines on the matrix that is not 0. It's called a pentadiagonal structure for a 2-dimensional Laplacian operator. If I get 3 dimensions, I would have 7, right? 2 more corresponding to, if I have ijk, they correspond to k plus 1, k minus 1 entries. But the structure will look like very similar. All right. Another way to look at the matrix is the matrix can be split into blocks. So let's split the vector and right-hand side into blocks. So the first block is going to be I equal to 1 block. The second block is I equal to 2 block. And etc. The last block is going to be I equal to n minus 1 block. So if I pair every block in U and every block in F, I would be looking at one particular block in the matrix, right? So for example, which block in the matrix corresponds to this first block in U, which means which block of matrix is going to be multiplied with this part of U and then going to be added with this block in F. It's going to be this block, right? Yes, this block is going to be multiplied with the first block in U and then get added to the second block in F, right? So that helps me divide the matrix into multiple blocks. This is block. Each block corresponds to a particular I index in the U solution and another I index in the F solution. So what you're going to see is that the diagonal blocks are tridiagonal structures as we have in the one-dimensional case. And there is going to be one non-zero block in the upper diagonal blocks and one non-zero block in the lower diagonal blocks. Right? This is again going to be, and each of the off-diagonal blocks are going to be diagonal. Right? That's kind of the structure of this finite difference matrix in 2D. All right, and I know this is going to be very unfamiliar in the beginning, but like one of the things I think you need to get familiar is how do you translate equations, a large array of equations, with some kind of rows and order into a matrix and visualize what the matrix is going to look like.